I'm going to go right into it. So do you mind slide? Yep. So this is the quintessential opportunistic mission science that I would highly encourage if you are a PI of a mission that was going to a surface of a planet, obviously the moon, but anywhere could do just fine, to use these inertial measurement units as a geophysics instrument. Heritage instruments are, can be used for science outside their original purpose. And if they're already on a mission and an IMU is going to be used by an engineering team for rover attitude and control, and this was also done pretty famously with JunoCam. There is no additional upmass to use an instrument for more than one purpose, and it only costs basically the cost of the computer programs and the staff. An IMU was used successfully for gravimetry in 2019, and the IMU that NASA uses is pretty standard across most missions. It is the Northrop Grumman LN-200S. It is already in space. We could, in theory, start doing seismology on Mars right now with the rovers that we have, and there has been gravimetry using Curiosity. Slide. So a little bit about the theory. Observed seismic data can be thought of as a convolution between the source function. So if you have a hammer, it's going to inject some energy into the ground and tracking that energy from the source itself. The rover response, so when you're smacking the ground with the rover's going to vibrate, somehow it's going to move on its own. So understanding how that rover moves. The instrument response, so it's going to have an instrument is going to have a noise floor. Everyone's seen an instrument that maybe glitches a little bit. Every instrument has its own personality. That's kind of what that response is. And understanding all of those three experimentally before flight lets us isolate the ground response, so which is the actual data we're looking for about what's going on in the subsurface. So how can we actually use an IMU to understand the shallow subsurface of the moon or a planet using seismology? Slide, please. So I'm going to do this as a series of benefits and drawbacks. So one, they're low cost and no added upmass. Slide. So this is a very rough estimate of the MSL's IMU as compared to a standard strong motion seismometer. The mass of a traditional strong motion seismometer can be upwards of 5 kilograms and take up something like 7,000 cubic centimeters of space. The standard LN-200S IMU that is already developed for space weighs less than 1 kilogram and only takes up a little bit more than 500 centimeters cubed. So when you're talking about space mission, you're going to want that smaller instrument, even if it maybe doesn't perform quite to the standards of what is traditionally used here on Earth. Slide. The other thing that's great is a wide dynamic range, because the strong motion is not going to saturate the IMU. Slide. So during Apollo, these are some plots from the Thumper experiment on Apollo 16. And you can see that all three instruments at some point during those Thumper shots was saturated. And this is even more, I don't want to say surprising, but it is the IMU would actually be on the rover mechanically coupled, whereas the geophones that measured this experiment were not actually co-located with their source. And so if they had been, the amplitudes would have been even higher, but they're already totally saturated. And once you have a saturated instrument, that initial source function is a lot more difficult to categorize. So an IMU is going to be able to capture that stronger source function a little bit better. Slide. For example, this is the Trident drill that is at Honeybee Robotics. We got to test it in its vacuum chamber out in Pasadena, and the larger than your average. Generally, ground motion is going to be less than 1 centimeter squared per second squared. We're talking like 4 meters per second squared, or even up to like 20 meters per second squared on a percussive hit. There's no way that a standard instrument is going to be able to record all of this kind of motion without being saturated. Slide. And not only that, the signal to noise ratio, even with that IMU that has a little bit of a high noise floor, is still between 300 and 200, and that source is still going to be up to 45 decibels above your background quiet. Slide. We also know that an IMU can be used to characterize basic geotechnical properties. So these are two spectrograms. One was taken with a forge wheel impact on basalt, one on tuff. With basalt, you have this strong peak and very little coda, so the energy all comes at once in this big peak. And it doesn't really matter how distant the IMU is from the source. That peak stays pretty stable when you hit basalt. Tuff, on the other hand, is a little bit more analogous to lunar surface material, and that energy doesn't peak in the same way, and it comes over a longer period of time, so it's a more attenuated source, or attenuated material. Slide. So there are some drawbacks. IMU data, traditionally, when used for engineering, is collected at pretty low frequencies, or it's averaged over several minutes, and also the IMU data is not traditionally shared with the science team. But the thing is, this is actually pretty easy to solve with conversations between the engineering and science teams. Before your mission launch, there is a discussion about how much data should we collect. So what sampling rate? How are we storing that data? How often is it being transmitted back? And also all of the rover the different responses of the rover, the instrument, and the source can be tested experimentally before launch. And during the mission, as your rover stops at different science stations where it would do measurements of maybe some spectrograms or maybe looking at other chemical materials, it's going to be doing drilling, scooping, hammering. Part of the data collection at each stop can be recording the IMU data at a higher frequency, between 100 hertz or 400 hertz, ideally. And that can be done for periods of time during those activities at science stations. Slides. Another issue we have is that the LN200S is actually ITAR data, so being able to acquire that data and put it on PDS might be a little bit of a challenge. Slide. But what's really wonderful about the CLIPS missions is that we're not just using our traditional LN200S. There are going to be different IMUs developed by different companies that are hopefully not protected by ITAR, so it'll be a lot easier to share some of that data to do seismic science with some of these missions. Slide. The other issue is that IMUs are not sensitive to the smallest ground motions. Slide, please. But we're working on modeling to see how Apollo era impacts, even their active seismic experience, might have looked on an IMU. And we're going to be using a couple of some more models of either maximum and minimum source sizes, using actual lunar surface properties in our modeling software. And again, if there are new IMUs that are being developed for other missions, it would be really great to characterize those before flight. Slide. So the key takeaway here is IMUs function as strong accelerometers strong motion accelerometers for no additional upmass. And while there are a few drawbacks as mission planning usually stands today, these can be pretty easily solved by stronger communication between the engineering and science teams. And with the opportunity with new missions, manufacturing different IMUs, having more data available, and hopefully an answer to the drawbacks of that small ground acceleration. We'll be able to talk a little bit more in detail about that at my next presentation. Slide. Thank you so much.